Thank you very much. The title of this session, of this workshop, is the role of optical wireless communication in the 6th generation of networks. And we've seen wonderful examples of how optical communication can play a role in connecting in the backbone network. But I would like to focus on the link to the end unit, to the subscriber unit, to all the IoT devices, of which there will be 1 per square meter in a 6th generation network. So it is about design considerations for sectorized beams. I explain why we like to sectorize beams in optical wireless communication links. And I would like to do that with the regards of my co-authors Paul van Voorthuisen, who is now with the semiconductor company NXP, and he used to be with Signify, Philips Lighting, now called Signify, and David Rojas with Signify. And I was also with Signify when we did quite some of this work. We borrow a lot of results in optical wireless communication from radio communication. And I see quite a lot of papers where we just use the equations and the models from radio communication, and then we design the systems and we hope that it works. And usually it works. But if we talk about standardization, we want to find an optimum. We want to prescribe what others should do. And then we want to be pretty sure that we're doing something that is close to optimum, that is repeatable, and that shows how we can move forward. And therefore, I would like to challenge you a bit with a field where radio communication is pretty different from what we see in optical communication. And the example that I'm taking today is what happens if you use a directional antenna. If you have a gain, G, then it doesn't matter whether you apply that gain at the transmitter or at the receiver. Your signal-to-noise ratio goes up by a factor of G. And therefore we like directional antennas. But that's no longer the case if we talk about optical communication. It becomes very tricky if we talk about how many sectors we use at the transmitter or at the receiver. So if we collimate the light, something happens that is different at the receiver or at the transmitter. So please keep this in mind when I'm talking about the rest of my presentation, and you will be confused. Or forget about this model, and then you may see how things are different in optical communication. Let's start with sectorization at the transmitter. We know that VCSEL arrays can use collimated beams exactly in the direction of the client device, and we can have a whole matrix of these VCSELs, so we can just pinpoint to the end user. And assume that I have n TX, n transmitter sectors. So I subdivide the coverage area into the sectors that I'm using here. And I'm talking about optical communication where we use intensity modulation. So it's the intensity of the light, but that gets converted into a current in the photodiode, and current squared is the signal-to-noise ratio. So what is happening is, if I only send all my power in an area 1 over n of the coverage area, the optical power goes up by a factor of n. So the current in my photodiode also goes up by a factor of n. And the signal-to-noise ratio goes up by n squared. Sounds a little bit like I'm violating the law of conservation of energy, because I chop up my area into n sectors and I get signal-to-noise ratios of n squared. But that has to do with the way that the optical detectors work. Now, the challenge is, already this is different from radio communication. At the receiver, it's yet another story. So let's assume that I have a certain die area of APD, area of the photodiode. And most likely this will work pretty well, because if I make that large, and Slim Louis just explained that we want to make it large, then I capture a lot of photons. So really get a large signal-to-noise ratio. But is that really the case? Is that really improving things, or can I do a sectorization? And with sectorization, we really have to make sure how we benchmark this. Coming from a manufacturer like Philips or Signify, we make a device, and the hole in that box, the optical opening area, is typically the constraint. Or on your smartphone, the area of the lens is what is concerning people. So the lens is limited, and if I just take these collimators, I have to subdivide my lens area into smaller sectors. And if I have sectors looking into separate directions, I capture less photons by making it directional. So my signal-to-noise ratio goes down rather than up if I use a non-imaging photodiode. But of course, we want to be smarter. And we don't need to use this facet eye like insects have, but if we go a little bit further in evolution, we have people, animals, with imaging detectors. And then we can keep the lens large. We can focus all the light into one point of the photodetector, and then I can split up my photodetector. And then it works because I have a large area that collects quite a lot of photons. But I do have an advantage because my photodiode is split in smaller areas. And by making it smaller, it will have a wider bandwidth. Photodiodes act as capacitors, and the smaller I make that piece of photodiode, the lower that detector is. So the imaging approach works, but I still like to go one step deeper by seeing how that effect of the photodiode now really helps, because I can get all the light by sectorizing, but I just gain, not in signal-to-noise ratio, but I gain in bandwidth. So at the receiver, by sectorizing, you gain bandwidth. At the transmitter, you gain in the square of the signal-to-noise ratio. And now here also an interesting observation comes when we are talking about standardization. Because we would like to standardize systems where we want to allow a different numbers of sectors at the transmitter compared to the number of sectors that I have at the receiver. You want to have that design freedom if we talk about a standard where we impose on everyone, you should do it this way. So let me quickly go through the design and signal-to-noise ratio. Signal-to-noise ratio is inversely proportional to the coverage area, A sub C, squared. And it is proportional, as I just explained, to the square of the number of sectors. If I chop it up, if I focus the light in one direction, I get n times larger currents, n squared times larger signal-to-noise ratio. In a non-imaging case, we have a certain area of the lens, ARX, A of the receiver, and if I increase that, I get in the square, I get more photons in. So signal-to-noise ratio goes with the square of ARX, and if I chop up the lens, signal-to-noise ratio goes down with n squared, because I just get fewer photons. But now there is a tricky thing here. The transimpedance amplifier gain I need to take into consideration, and the noise from that transimpedance amplifier. And that is where, in addition to what Slim just said about the size of the photodiode, I would like to show a further sophistication of that model. Scary bit of math, but I will explain. Signal-to-noise ratio is proportional to some effects at the transmitter, n of tx divided over A sub c squared. I also already had the area of the receiver divided by the number of segments at the receiver squared. Then in the numerator, I have my signal strength, and in the denominator, I do have the noise. But what typical transimpedance amplifiers do is they flatten the response of the photodiode by just boosting the signal if there is some effect of the capacitance. So you don't see the limited bandwidth in the signal, but the noise goes up. And I'm not going into the details of the electronics, but what you typically see that in addition to the noise spectral density, I also have a term where quadratically the noise goes up because of the effect of the photo amplifier. And what I see here is that basically, depending on how I choose that bandwidth, I get more signal to, I get more noise. But if I just take a limit where we use a lot of bandwidth and push that bandwidth beyond the bandwidth where that noise goes up, I can forget about the first term, and it is bandwidth to the power cube. And if I then remove all the things that are constants, I get a relatively simple expression. Signal to noise ratio is proportional to the number of sectors at the transmitter, inversely proportional to the number of sectors by which I chop up my lens, and again proportional to the number of sectors in which I chop up my photodiode if I use an imaging detector. So the lesson here is things are a bit tricky. And when we do standardization, we have to allow for innovation just in the year after we have set that standard. So we need to have that flexibility. And a lot of the stories in the paper, and I will try to cut short a bit my presentation not to dwell too long, is how can we design a system such that I can have an arbitrary large number of sectors at the transmitter, because that helps, and I can just lose a small number of detectors at the receiver, maybe just one detector. So that imbalance requires a kind of feedback loop, where we have a single detector that detects one of the signals coming from one of the sectors. And the whole idea is that we embed a code per sector that allows the receiver on the other side to detect which sector is actually imposing the light on the counter station. And via a small feedback channel, that information is sent back. Now, in order to design that system, we did a test, we built it. The mechanics are here just to shake up the whole system, not to steer the beam. The beam steering is because of the 13 LEDs that transmit in different angles, and we just have a single photodiode that looks into these directions. So we have a number of sectors. We transmit an identifier in parallel, synchronously, and the way of encoding that we use there is to use a Walsh-Hadamard code. Every sector uses one of these Walsh-Hadamard codes. The Walsh-Hadamard codes are described here. They are 1111, that's one of the codes, which we're not using here. And then we are just a construction of 1 minus 1, 1 minus 1, of building that code. So it is a set of purely orthogonal codes, which I can perfectly separate. And therefore, the detector on the other side can just measure what comes from which detector. But then I still need a synchronization. And in order to get the synchronization, we scramble the whole signal with a linear feedback shift register code. And that allows me to do the synchronization. So the detector then becomes very simple. I synchronize with the linear feedback shift register code. Then we do a single Walsh-Hadamard matrix, which is a simple butterfly structure. And I get from all the sectors exactly the signal strength that comes in from that sector. So that leads to a relatively simple design of the system where I can show how the metrics work. But I will not go into the details. I will just invite you to read the paper. There are questions from reviewers. I can answer these, or I can answer questions from the audience. You prefer from the audience. So then I end with my conclusions. A lot of research work in optical wireless communication is about establishing a speed record. That's like building a Formula One racing car. But that is not the design that influences your car on the street to get through congested traffic in Mumbai. There you design for repeatability, for interoperability, and that's where you need to design. So on the right-hand side, people say, I've shown it in a lab, that's a proof. And if you just do something on reference models, you haven't shown it in reality. If you go to the left-hand side, that's where the radio community would say, you've showed it once in the lab. Does that work for the millions of devices out in the street? No. You should use reference models, because these have been established by the community. And that's where we see a bit of tension, a bit of different cultures in this field. And as you may understand, I'm a little bit more on the right-hand side than on the Max Verstappen side today. Okay, so what did the reviewers say when they saw this paper? Maybe a good tradition in conferences to get back to what reviewers said. How about multipath? Well, there is the main link data, so I will not address this, but for our system of establishing which sector is working. We clock this additional signal relatively slowly at about 100 kilohertz. And any multipath in terms of delay spread will not affect the signal. But there is multipath possibly in terms of an angular spread, a reflection that goes to a wall. Well, that's exactly what these orthogonal codes can separate. So if there is an angular spread, the receiver will just measure how much signal comes in via what kind of sector. And then you can do optimal comparison, optimal loading of the different sectors. Does the separation between the LEDs have an impact on performance? Well, if there's overlap between two sectors, the receiver will see two of these pilot signals. And it will say, this one has a strength of minus 10 dB and the other one of minus 12 dB. And it will just give that as a feedback to the receiver. So overlap and smooth handovers when you switch from one sector to another can perfectly be handled by this scheme. Then there is a question about the potential misalignment between the transmitter and the receiver. Well, my point exactly is, we started off with this design to separate that there need to be any alignment. There may even be a different set of sectors, 15 sectors, or let's say 256 by 256 VCSELs, all acting as a separate sector, and just one detector. So that can be completely separated, thereby you can make it flat, you can integrate it, and there is no factory alignment or AI algorithm that connects sectors at the receiver to sectors at the detector. Well, it was a thing that was tested and built by David Rojas at Signify. The implementation of the algorithms was done by Paul van Voorthuisen, and it has been tested really on the road as a proposed product of Signify.